Hi, it's time to start today's afternoon session. And the first speaker is Matsuo-san from Nagoya University. He will talk about on lattice gauge theory and the discretization of Dirac operators. So please start.
Thank you very much for the introduction. I'm Shinichiro Matsuo from Nagoya University.
Time to start today's afternoon session.
Can you hear me? Okay. The title of my talk is Lattice Gauge Theory and the Discretization of Dirac Operators. And this is a joint work with, just a moment. My place doesn't work. And this talk is based on a joint work with Hidenori Fukaya and Tetsuya Onogi and Satoshi Yamaguchi. And these three are physicists. And this is also a joint work. This is also joint work with Mikio Furuta and Mayuko Yamashita. And these three, these two, including me, is a mathematicians. And so this talk is based on a joint work with three physicists and three mathematicians. And let's start with stating our main theorems. Now, details are given later. For A, positive, and very, very small, we have the index of a twisted Dirac operator D on flat tori. D-dimensional flat tori is thus R over Z to the D is equal to the index of the Wilson-Dirac operator, which will be explained later, denoted by dW, on discrete lattice. We denote it by T hat, and defined by AZ over Z to the D. This is the main, and the same holds for Clifford index and the family index. And this is the main theorem. And why I'd like to explain why this is interesting, because index, Fredholm index, is purely infinite dimensional object, but the discrete lattice AZ over Z is just a finite number of points. So Wilson-Dirac operator is just a finite dimensional object. So its index is always, so its naive index is always 0. So giving a meaningful index to the Wilson-Dirac operator is also a problem.
So, San, can you hear
Yes.
me? One question. T hat, is this definition correct?
Yes.
Z. Is it over Z?
Yeah, AZ over Z.
Small
Just
sum.
point is A, and this is 1. This is a T hat. And any other questions? And this is, as I said to you, joint work with these people. And my motivation, my motivation is come from Zybagwitten theory. And diff is equal to PL in dimension 4. But I do not explain my motivation any further. I'd like to talk concept on just the content of my main theorem. This is a main theorem, and I'd like to explain why this is interesting in this talk. Okay. Now let's start with the brief review of index and spectral flow and K theory. Index, spectral flow, and K theory. So for simplicity in this talk, we assume D is even. D is a dimension of tori, and let's TD be a flat torus, D-dimensional torus. And let E be a bundle on A, Hermitian. And Z2 graded Clifford module bundle or module bundle, which means there exists bundle map gamma from E to E, and also bundle map Cj from E to E, and J goes from 1 to D, and such that gamma is self-adjoint. Gamma is equal to gamma star, and gamma squared is equal to identity, and Cj is Q adjoint, and Cj squared is equal to minus identity. And Ci and Cj anti-commute if Cj and Ci and J are not equal. And also gamma and Cj anti-commutes. That is gamma Ci, Cj plus Cj, gamma is equal to 0. This is a definition with its graded Clifford modules. Okay. And using these data, and also we fix a connection nabla on the bundle. We can define a Dirac operator D from gamma E, the section of E to gamma E, by D phi is defined to be Cj times nabla J phi J to T. This is a definition of Dirac operator. So let me give you some example. When D equal to 2, we can take gamma is equal to 1, 0, 0, minus 1, and C1 is equal to, for example, 0, 1, minus 1, 0, and C2 is equal to 0, I, 0. Then gamma and C1, C2 satisfy this relation. Gamma is self-adjoint and square to 0, and C1 is skew-adjoint, C2 is also skew-adjoint and square to minus identity, and they anti-commutes. Then, in this situation, D is, by definition, C1 times ddx plus C2 ddy. And this is just 0 ddx plus I ddy minus ddx plus I ddy and 0. And this is essentially a Dirac-Cauchy-Riemann operator. Twice Cauchy-Riemann operator, and this is its adjoint. So Dirac operator is just a generalization of Dirac Cauchy-Riemann operators. Okay, and this has two essential properties. D is self-adjoint. Self-adjoint. And odd, which means D is equal to its adjoint. And D is odd if D gamma times plus gamma D is equal to 0. D and gamma anti-commutes. And gamma gives this grading to E. Okay. And using data, we can say the following. If d phi is equal to lambda phi, so lambda is eigenvalue, then d of gamma phi is equal to, using these anti-commutation relations, minus gamma d times phi, minus gamma d phi, and d phi is equal to minus lambda phi, equal to lambda phi, so this is equal to minus gamma lambda phi, and lambda is just a real number because this is self-adjoint, so this is equal to minus lambda times gamma phi. So this means that if lambda is eigenvalue, then minus lambda is also an eigenvalue. So spectrum D is symmetric around the origin. So if this is lambda, then this is 0. If lambda is an eigenvalue, then minus lambda is also an eigenvalue. And minus 0 is also 0. So gamma acts on kernel D. And because torus is finite dimensional, because D is compact, because torus is compact, this kernel D is finite dimensional. So using these observations, we can define the spectrum index of D. Definition. Index of D is defined to be trace of gamma restricted to kernel D. So D is an infinite dimensional object, but kernel D is of finite dimension, and this trace is just a trace. And this is nothing but dimension of phi, which satisfies d phi is equal to 0 and gamma phi is equal to phi minus dimension of phi, which satisfies d phi is equal to 0 and gamma phi is equal to minus phi. So index of D is a supertrace of gamma. And this is, you can check that this coincides with the usual Fred-Moulty index. Then next, I'd like to explain spectral flow and its relation to this index. Next, we consider a family D plus M gamma. Gamma is a grading operator for E for M in -1 to 1. And if we consider the square of D plus M gamma, then it is equal to D squared plus M times D gamma plus gamma D plus M squared and gamma squared. And D and gamma anti-commutes. So this is equal to 0. And gamma squared is equal to identity. So D plus M gamma squared is just D squared plus M squared. So using this computation, we can see that spectrum of D plus M gamma is equal to the following set: plus and minus lambda squared plus M squared. And lambda is in spectrum of D. Okay. Now we can write a picture of spectrum. This is M direction, and this is a spectrum direction. And when M is equal to 0, D plus M is equal to D, and so there is a spectrum lambda. And if there is a lambda, there is also minus lambda. And the symmetry is given by gamma minus lambda. And there may be a 0 eigenvalue. And we can say that square D plus M gamma is like this. Lambda squared plus M squared. And also, if there is zero eigenvalue, we have the following line. Okay, this is a picture of spectrum D plus M. Okay. Next, we consider the multiplicity of these orange line and blue lines. If, in order to consider the multiplicity of these two lines, we will compute the following. We have a following observation. If d phi is equal to 0 and gamma phi is plus or minus phi, then D plus M gamma phi is equal to plus or minus phi, M phi, of course. So using this trivial computation, we can show that multiplicity of this blue line, multiplicity, is equal to dimension of phi, which satisfy d phi is equal to 0, and gamma phi is equal to plus phi. And in the same way, the multiplicity of this orange line is equal to dimension of phi, d phi is equal to 0, and gamma phi is equal to minus phi. So let me recall that the definition of index this is a definition of index, and this is equal to the multiplicity of the blue line, and this one is equal to the multiplicity of orange line. So from these observations, we define a number of multiplicity of blue line and multiplicity of blue line minus multiplicity of orange line is equal to the index of D. And we define this number to be the spectral flow of the family D plus M gamma. Spectral flow. So I explained that spectral flow of D plus M gamma is equal to index of D. This is closely related to the suspension isomorphism of K theory. That K0 of point is isomorphic to K1 of the relative K1 of this interval, and index lives here, index of D, and spectral flow lives here. And these two are equal by suspension homomorphisms. Okay. Next, I'd like to explain the Dirac operator on the lattice. Dirac operator on the lattice. Lattice. Fix n, natural number n, and let A to be the 1 over n. And so n is very big. And we consider regular lattice, T hat D, which is defined to be a z over z to the d. And let E hat to be just the restriction of E to T hat, and which is a discrete vector bundle on T hat. Okay. And using parallel transport, of,
Excuse me.
yes.
What is the definition of E hat before restriction?
So sorry. E hat, sorry. Thank you very much. E hat is just a restriction of E. Thank you very much. And using parallel transport of E nabla on E, we can define D hat JF of phi is equal to phi at x is equal to x plus a EJ. Oh, EJ is a fundamental vector. Minus phi x divided by a, and for x in T hat. And DJ, strictly speaking, this is parallel transport on E. And also we can define the B. B means backward and F means forward to be phi x minus phi x minus a EJ divided by a. And we can show that the adjoint of TJ nabla J hat F is equal to minus of nabla J B hat. And we define a lattice covariant derivative by what the following. Lattice covariant derivative by D, which we denote the lambda J hat to be lambda J hat F plus nabla J hat B divided by 2. Then nabla J hat is skew adjoint as usual, differential operator. And using these data, we can define a naive Dirac operator by which we denote D hat to be Cj times nabla J hat as in the usual continuous Dirac operators. And then this satisfies D hat star is D hat, and which anti-commutes with gamma. But so that we can define as index as usual, but index is always 0. This is very, very bad news. Because you can easily check that dimension of gamma E hat is of course, finite dimension because discretized torus is just a finite number of points. And gamma gives an isomorphism from E plus to E minus. E plus is a plus eigenvalue of gamma, eigenspace of gamma, and on E minus, gamma is equal to -1. So using these two observations, we can show that the index of the hat is always 0. So there is a Dirac operator which has non-zero index. So index D is not index of the hat in general. So that's about the situation. Okay. Next, then here comes the Wilson-Dirac operators. Wilson-Dirac. We define the mysterious Wilson term by Wilson term, by which we denote W, which was defined A over 2 times gamma times J equal to 1 to D, and D J hat F star DJ hat F. This is a definition of Wilson term. And the very important remark is no continuous counterpart. So this is just a lattice phenomena. And we can show that W is self-adjoint. And W is not odd. W commutes with gamma. W is not odd. And using this Wilson term, we can show that. We can define what? Naive Dirac operator here is not a good operator because index D hat is always 0. And we introduced Wilson term, mysterious Wilson term. And then we define the Wilson Dirac operator. To be, which we denote DW, to be the sum of the naive Dirac operator and W, Wilson term. This is a just definition of W, Wilson Dirac operator. And then DW is self-adjoint. But Wilson term, as I said to you, Wilson term is not odd, so DW is not odd. So we cannot define the index of DW directly. Then we use the spectral flow. Thus, it is not so obvious to define the index of DW. And then we use spectral flow. And for A, positive and very, very small, index of DW to be the spectral flow of DW plus M gamma. And M is in -1 and 1. This is the definition. But in order to be well defined, this definition to be well defined, we need the following theorem. So this is also our theorem. For A, there exists a node, which is of the form A and the node. For any A smaller than a node, A is of the form of 1 over n, which is between 0 and a node, such that dw plus M gamma is invertible at the end point. M is equal to +1 and M is equal to -1. For continuous theory, this is obvious, but on lattice, this is not obvious, but it is anyway true. And using this term, we can define the spectral flow of this family. And now, finally, we can restate our main theorem. And let me summarize our situation. We first fix Clifford module bundle on flat torus. And D is the Dirac operator, which will define Cj times number J, and we can define index of D. And this is a continuous situation. And we discretize this situation, E hat on T hat. And T hat is just AZ over Z, and A is very, very small. And E hat is a restriction of E on T hat. And D hat, naive Dirac operator, which is not a good operator, but Cj times lattice covariant Dirac operator. And we introduce Wilson term by and we define the Wilson Dirac operator to be the sum of the hat and Wilson term. And we define index of DW to be the sum spectral flow of DW plus M gamma. And there is a suspension homomorphism from K0 point to K1, relative K1, or minus 1, 1. And index of D lives here. And spectral flow of D plus M gamma lives here, and which is equal. And the spectral flow of D plus DW plus M gamma lives also in K1. Sorry, this is K1. And the index of DW is defined to be this spectral flow. This is our situation. And the main theorem is there exists a node. And so for any A, which is smaller than a node, we have index of D is equal to index of DW. And the same holds for Clifford index and family index. That's all. Thank you very much.
Thank you. And is there any question or comments on site? How about from online? Is there any question or comments? From on site, Chris-san. Chris.
Yeah, this is Chris Bowen from Nagoya. Maybe if I talk here, it's better. Okay. Can you go back to where you define the index of the Wilson-Dirac as the spectral flow?
Yes.
I may be a little confused because, oh, sorry, I see now. So I missed, because yeah, if the operator is invertible, then its spectral flow vanishes, but you're saying that M at the points plus or minus 1, the operator is invertible.
Invertible only at the end point.
Okay, great. But I guess you could also, instead of taking a very, very small a, you take a very, very large but finite m. Would that, I guess you would get the same, you would still get an invertible.
Yeah, if we fix a and we take a very, very large m, it's true.
Okay, yes, thank you.
Thank you very much for the question.
I have one question. Yanagida です。はい。
Yes.
So, yeah, so how the Wilson-Dirac operator is introduced by your collaboration, or
A Wilson-Dirac operator is introduced by Wilson.
by
Wilson,
Yeah.
famous Wilson renormalization group. Wilson.
Yeah, but this sorry. So this DW is already known one.
Yeah, this DW is already known and very, very famous. This is related to doubling phenomena in lattice gauge theory, or in condensed matter physics. This is closely related to Nielsen-Ninomiya theorem.
So the new point is that the definition of the index as a set.
New point is actually a theorem, the proof of theorem. And the very new point is this: the same holds for Clifford index, family index, and group index, equivalent index. Index. The new point is this, and the method of proof.
Oh, I see. Thank you. Is there any other question or comments? So then let us thank Matsuo-san again. So thank you very much.
Thank you very much.
So the next talk will start on time. So, I think 5 minutes later. Yeah, from 3:20 in Japan time and 2:20 in China time.
So maybe next speaker can prepare. Who is the next speaker?
Yes, Hao-san, Hao-fu-san.
How Shu, not Fu.
Sorry.
Oh, yeah, it's me. Can you
You can see
see me? Yeah,
Yes.
okay. Let me share my screen.
screen.
Let's see. Okay.
Yes, we can see you. Okay. I think it's time to start the next talk. The next talk is by Professor Xu from Göttingen. He will talk about from group cohomology to topological quantum invariance. So please start.
Okay, thank you for the introduction. I would like to thank the organizer for the invitation. So today my title is Group Cohomology and its generalization to topological quantum invariance. So So we will start from something very humble. So suppose we have a finite group G, and we can consider it a group ring. So this is a free abelian group generated by elements in G, and it has a multiplication induced by group multiplication on G. Then we can consider the so-called bar resolution. So this is a non-exact sequence of free G modules where, so you can see, so on the 0th degree, you have Z with a trivial G action. And on degree 1, you have the group ring itself with the canonical G action. And then on the degree n, you would have n copies, tensor product of that G. And its differential is defined in this way. So you eliminate the case entry of the pure tensor and summing over these differentials. So using bar resolution, we can define group cohomology and group homology. So group cohomology is defined to be the derived functor of this functor. So in particular, we can take tensor product of the bar resolution with a given G module M, and it will give me a non-exact sequence back. And then I take the homology of this chain complex. Sorry, no, not non-exact sequence. You will get a chain complex, and you can take homology of that. And for group cohomology, I take the home functor from this bar resolution to a given G module, and I will get a cochain complex. So I can take cohomology of that. So this is definition of group homology and group cohomology. And then by definition, we see that on the 0th degree, you have, so the group cohomology, you have on 0th degree, it is exactly the group coinvariance, or in other words, it is the collection of orbits of the G action on M. On the other hand, the 0th degree of group cohomology, which is the map from trivial module to M, which preserves G action, that is exactly the fixed point of the G action on M. So by definition, you can also compute. So for simplicity, let's look at low degree group cohomology. What does it gives us? So the first group cohomology is a collection of group homomorphisms from G to M. Okay. Well, second group cohomology becomes more interesting. So it controls the central extension of G by abelian group M. So let me recall some terminology. So extension of group means we have another group, G hat, and you would have an injective group homomorphism from M into G hat, and you will have a projection group, a surjective group homomorphism from G hat to G, such that we require this exact condition. So the kernel of the projection equals the image of the embedding. Well, such an extension is called trivial if this G hat is isomorphic to the direct sum of this group M with G. And we say this extension splits if you can find a section S of the projection P. And well, in this case, the group extension is characterized by the so-called semi-direct product of the group M with G. And finally, we say this extension is central extension if the abelian group M sits inside the center of group G hat. Okay. Well, we can understand higher group cohomology from the perspective of algebraic topology. So the story is this: so given any group G, possibly with topological structure, there is a connected topological space or a pointed topological space called Eilenberg-MacLane space, denoted by KG1. So this space is determined unique up to homotopy equivalence. And it has a property that if you take the fundamental group of this pointed space, you will get back your group G. Well, this is the case if G is discrete. If G is a topological group, then the situation is more complicated. So in the case that G is discrete, the higher homotopy of this Eilenberg-MacLane space vanishes. Also, if G is abelian, then you can form the so-called higher degree Eilenberg-MacLane space, denoted by this KGN. And it has a property that if you take the nth homotopy group, then you get the abelian group G, and other homotopy group of this space must vanish. So just for notation, I will also use BNG or simply G bracket N to denote this Eilenberg-MacLane space. Well, this notion means something called delooping in algebraic topology. Okay. So let me give you some examples of Eilenberg-MacLane space. So these are all examples at degree 1. So for abelian group Z under addition, its Eilenberg-MacLane space is given by circle. So it's a quite well-known fact in algebraic topology that the fundamental group of circle is Z. Well, if I consider Z mod 2, its Eilenberg-MacLane space is modeled by the so-called infinite dimensional real projective space. So you can imagine it as, so you have a unit sphere in the infinite dimensional Euclidean space R infinity. And it turns out this space is contractible. So, and on the other hand, you can just consider the collection of R1, the real line, passing through this unit sphere. And it induces Z2 action, which is free and transitive. So its quotient, which is R infinity, RP infinity, is a model for Eilenberg-MacLane space of Z2. Well, the third example is Eilenberg-MacLane space for U1. So here, the circle group U1 is viewed as a topological group. So it has a topological structure. And it's given by this CP infinity. So it's a complex projective, infinity dimensional projective space. And in the same manner, but it is induced by, so you have a fibration from the 2n+1 dimensional sphere to this n-dimensional complex projective space, and it always has fiber U1. So when this n tends to infinity, in other words, if you take the colimit of these fibers, you still get U1. So CP infinity is a quotient of this infinite dimensional sphere by U1 in some sense. So, okay. So why do we introduce Eilenberg-MacLane space? Well, that is because now we can characterize group cohomology and group homology, which was originally defined using some algebraic definition. Now it can be realized by this topological construction. So it is actually equivalent to take singular homology or singular cohomology of these Eilenberg-MacLane space. In particular, the group homology is a singular group it's a singular homology of the Eilenberg-MacLane space, BG, and similarly for cohomology. So we have this nice result, and then we can reconsider what it means for this low degree group cohomology. Well, we see that for example, the first group cohomology, now it's given by the connected component of pointed maps between BG and BM. Well, this is exactly the group homomorphisms from G to M. Well, the second group cohomology now is a pointed map from BG into twice delooping of M. Now this can be viewed as a homomorphism, not between one groups, but between two groups. So this should be viewed as, if you like, it's a continuous map from this G to this BM. So it's a two group. And another way to view this is, so from this C, I can form this fiber sequence. So I take this fiber, and this fiber turns out to be G hat is a central extension of G by M. Now this story can be generalized to higher degree group cohomology. So if I suppose my G is a connected topological group, then I can take this iterated fibers. So I have very long fiber sequence. So at the bottom is our given K cocycle on G, viewed as a continuous map between K groups. And then I just take its fiber and fiber and fiber again. So now at the top level, I see this is the same as considering central extension of this K-2 looping of this group G by M. So it's central extension of this group by M. Well, now you may ask, why do I need my group to be connected? What happens if my group is discrete? Well, if your group is discrete, then it's looping. In particular, you take loops in this group, which is based loop. So it has to be based on the identity element. And the base loop of a discrete group is trivial by definition, which is not what we want. So here brings the question that how do I characterize the higher group cohomology if G is a discrete group? Well, the short answer is I should consider central extension of G by this K-1 group. So if G is discrete, one should imagine this is a bundle over this discrete set G with fiber, which looks like the K-2 delooping of M. That is, we have a direct sum of G copies of M delooped K-2 times. In this case, the group homology data corresponds exactly to the induced k-1 group on this whole extension. To obtain a more conceptual understanding, we need to take a detour into higher categories. And from now on, let's, for simplicity, fix a coefficient n just to be the complex numbers, invertible complex numbers under addition, under multiplication. And then given a two-group cocycle gamma, I can form the so-called gamma-twisted group algebra. So this is just a group algebra with additional coefficient given by this gamma. And you can check that if I add another coboundary to this cocycle, then I obtain the same algebra up to isomorphism. And we can denote its category of modules to be this rep G gamma. So, well, in the language of physics, this gamma kind of represent the Hopf anomaly in some systems, topological quantum systems with global G symmetry. But sorry, because of constraint of time, I cannot go into details on that point. So this is related to this notion called projective representation. So you will see a projective representation is, by definition, you have a map from a group G into GLV such that its action now is not associative, well, is associative, but with additional phase. And the associativity of this group G implies that this coefficient gamma is a group 2 cocycle, and then unitality and inverse of G impose some further renormalization conditions on that. But in summary, you see that projective G representations and their morphisms form a linear category. And it has been just be the direct sum of these representations of twisted group algebra. And moreover, I can take tensor product of projective representations, and that would induce a rep G action, categorical action on this projective G representations. Well, since rep G is a symmetric tensor 1 category, its module category form a tensor 2 category. And this tensor 2 category is an equivalent model for 2 representations of group G. So 2 representations is defined in this way. So I take the functors from BG into 2-vec, the category 2 vector spaces, which is just a categorification of 1 representation. So the abelian group structure of the second group cohomology is reflected in the product rule, fusion rule for these 2 representations, for these projective G representations viewed as 2 representations. Well, in general, you can define the notion of multifusion N category. So I just quickly show you what it should have. So you should have a monoidal structure, it should have a linear structure, and you should be able to take direct sums, and it should be Karogi complete in the sense that it's idempotent complete and is separable and rigid. With all these nice properties, you can define N representations of group G. So it's just the category of functors from BG into the category of N vector space, which is itself a fusion N category. And then given a n+2 cocycle, I can define the categorified twisted group algebra just in the same manner. And their category of modules would form n+1 category, which is kind of a projective N representations. Sorry, it should be projective n+1 representations of this group G. And similarly, the tensor product of these projective representations would give me that, so this n+1 category can be viewed as n+1 representations for my group G. Okay, now the conclusion is that given a finite group G, its higher group cohomology provides some examples of higher representations. And this is what I mean by topological quantum invariance. But in general, the n representations can be beyond just the group cohomology on G. So there's, for example, in symmetry, breaking. So in physics, you can consider a system with symmetry G break into some subgroup H with some de Hooft anomaly, and that would be corresponding in the case to these higher n representations. And also you can consider inclusion of vacuum into, so it gives you some trivial representation of group G. And in general, you can stacking and coupling between these two types and give you a new n representations of group G. So due to a limit of time, I need to stop here, but I want to mention that you can also have these applications of group cohomology in all kinds of areas like TQFTs, theory of topological orders in condensed matter physics. Recently, it also appears in classify topological operators in genuine QFTs. And hopefully it will also give us some novel quantum invariants in quantum computing theory as well. So I will stop here and thank you for your attention.
Thank you for the clear talk. And is there any question or comments from Nagoya?
Sorry, I have one question. Can I ask
Yes.
you? So, I'm interested in the relationship between the projective representation and second cohomology. So second cohomology is related to the central extension.
Yes.
So, but you, in the later part, you discussed something in this slide, but I could not follow because of course, once we fixed one central extension, then we have some factor system. So factor system is somehow some phase factor related to the gamma is a factor system. So once we fix the gamma, so then we have a one central extension, I think. Of course, in
Yes.
that case, we need to divide some equivalent relationship. So then, but later you discuss the relationship with category, but I could not understand that part. That part is somehow very abstract.
Oh, yeah. I must apology that I don't have so much time, so I just rushed through this a bit, and it's okay. I would say it's just it's a direct categorification of the case happening in n equals 0. So if you replace n here by 0, and you should see this very familiar story in the 2 cocycle case. So 2 cocycle. So I give in detail that these 2 cocycle give you some 2 representations. And this is because this category of
No, I cannot understand. What is 2 representation?
Yeah, so the category of projective representation. So I'm not consider a single projective representation, but a collection of all projective representation with the same cocycle. And this collection of information give you a 2 representation. And this situation can be generalized to higher degree cohomology, but now you should have higher categories instead of just one category. And so that is the message I want to deliver here. Does that solve your question?
So, still I could not understand what is the two representation.
Yeah, so by definition, the n representation is functors from BG into this category of n vector spaces. So this is an n category. The target is the n category. And in the case n equals 2, this target is a 2 category. So why is it a representation? Because for n equals 1, a G representation is exactly a functor from BG. So you have a single point and morphisms is labeled by G. You send this category into the category of vector spaces. So this is representation of G. And for 2 representations, I need to categorify my target to be the 2-vec. So
Still I could not understand 2-vec. So this is what is 2-vec? Maybe you already defined previous part.
yes, so okay, so it's as I said, you have several equivalent models for 2-rep. So one model is that you can consider linear categories with categorical G actions. Or you can consider algebras with G actions, but these are algebras up to Morita equivalence. So you can consider G algebras with G bimodules and bimodule homomorphisms. That is also a model for these 2 representations. And in general, here I'm considering another model. So its object is the module categories over rep-G, and its product is this so-called relative limit tensor product. So yeah, I would say there's several different models for these 2 representations. So I'm being a little vague here about what I really means, but they should be all equivalent. And does that solve your question, or is it still unclear?
So, no, so quite difficult for me. So also maybe it is quite difficult to explain everything now. So maybe
I must apologize for this compact.
move to another question. So Yanagida-san, please ask another question. I stop question now.
I see. So is there any other question? Then let us thank Shou-san again. Thank you very much.
Okay. And I stop sharing. Okay. Yeah. Thank you.
The next speaker is Hayami-san, and Hayami-san is no.
Can you hear me?
Yes, yes. You can share the screen. Okay. Yes. Now it's time to start the final talk of today's afternoon session. So the speaker is Hayami-san from Nagoya, and he will talk about DG symplectic geometry and higher Poisson vertex algebras. So please start.
Thank you for introduction. And today's talk is DG symplectic geometry and higher Poisson vertex algebras. But today's talk is about the symplectic geometry and how to use the DG symplectic geometry to get a higher notion of Poisson vertex algebras. First, I will introduce DG symplectic geometry. In usual geometry, smooth functions over smooth manifold form a commutative algebra. In differential graded geometry, replace the commutative algebra by a differential graded commutative algebra. And for example, we consider the shifted tangent bundle of this form. And this one means the degree shifting of the fibers of the vector bundle. The functions of this shifted tangent bundle is the Durand complex of the base manifold M. And the functions of the shifted tangent bundle is a differential graded commutative algebra where the Durand differential is D, is a convergent vector field on D1M. And DG symplectic geometry is the symplectic geometry in the DG setting. This is a definition of a DG symplectic manifold. First, M is a locally ringed space, which is locally isomorphic to U, and the ordinary functions of U tensor a symmetric V star where V is the finite dimensional graded vector space and star is the dual, and symmetric means the graded symmetric algebras. So graded manifold M is a locally ringed space, which is the first function is a graded commutative algebra. And omega is a graded symplectic form of degree K on M. Graded symplectic form means closed non-degenerate to form. And we can define a degree minus n Poisson bracket on the functions of M via this form, where XF is the unique graded vector field that satisfies this formula. And XF is called a Hamiltonian vector field of F. And a DG symplectic manifold is a suitable. M is a graded manifold, omega is a graded symplectic form, and S is a function called Hamiltonian on C of the functions of M, such that the degree of S equal n plus 1, and the Poisson brackets of S and S equal 0. This equation is called the classical master equation. And using S, we can define a differential on the functions of M by the Hamiltonian function and the Poisson brackets of the form. The degree of S equal n plus 1 is equivalent to the degree of Q equal 1, and the classical master equation is equivalent to the nilpotency of Q. And so using Q, C infinity M becomes a differential graded commutative algebra. This is the definition of a DG-symplectic manifold. And DG-symplectic manifold has three important properties. First, it is a mathematical counterpart of BBA formalism and BFB formalism in theoretical physics. BB formalism is a homological formalism for treating general gate theories. And in terms of DG-symplectic geometry, the space of a BB fields can be seen as the infinite dimensional graded manifold, and BB anti-brackets and BRST operator BB action corresponds to the BB anti-bracket corresponds to the Poisson brackets. BRST operator corresponds to the homological vector field. The BB action corresponds to the function S satisfying classical master equation. So, BB formalism can be seen as infinite dimensional DG-symplectic manifolds. And the second property is some important structures such as Poisson manifolds and Courant algebras can be encoded in DG geometric structure. First, we see Poisson manifolds. A Poisson bracket on the manifold M is a bilinear operation satisfying the skew symmetry, Jacobi identity, and the Leibniz identity. A manifold equipped with the Poisson bracket is a Poisson manifold. We see there is a one-to-one correspondence between isomorphism class of DG-symplectic manifolds of degree 1 and the isomorphism class of Poisson manifolds. For degree 1 DG-symplectic manifold, denote Ci C infinity M by the degree I part of the functions of M. Then degree 0 parts of C infinity M is identified with the functions of the base manifold. For degree 0 parts of the functions, we consider the bracket of this form. So when M omega S is the degree 1 DG-symplectic manifold, this bracket encodes a Poisson manifold structure. The bracket of this form is called the derived bracket. As there is one-to-one correspondence between isomorphism class of DG-symplectic manifolds of degree 1 and isomorphism class of Poisson manifolds. Next, we see Courant algebras. A Courant algebra is a vector bundle E over smooth manifold M with a bilinear form and bilinear bracket and the anchor map satisfying a set of compatibility conditions. And the most important example is the Dorfman bracket on the generalized tangent bundle. The pairing and the Dorfman bracket is given by this formulas. For degree 2 DG-symplectic manifold, they can encode the structure of a Courant algebra. For degree 2 DG-symplectic manifold, denote Ci C infinity M is a degree I part of the functions. Then a degree 0 part is identified with the functions of the base manifold, and the degree 1 part of the functions is identified with the sections of the vector bundle. Therefore, the functions of the base manifold and for the sections of the vector bundle, we define the pairing and the bilinear brackets by these formulas. So this computation gives a digit-symplectic manifold of degree 2, the structure of a Courant algebra. Anchor map and the bilinear bracket is made by the derived bracket, and the pairing is made by the Poisson bracket. And these symplectic manifolds of degree 2 are in one-to-one correspondence with Courant algebras. Just important properties is that using these geometric techniques, we can make topological field theories and currents in a uniform way. AKLC sigma models are n+1 dimensional topological field theories whose target data are degree and digit symplectic manifolds, including Poisson sigma models and Chern-Simons sigma models. And BFV current algebras are n-1 dimensional current algebras whose target data are degree and digit symplectic manifolds. And this is the key item of today's talk. So I will explain now. So next section, I will explain the BFV currents. Current algebras are Poisson algebras consisting of functions on mapping spaces. For example, Alexey-Strobel current algebras are current algebras on the cotangent space of the loop space. The currents are of the form, and the Poisson bracket is given by the second formula. And the key point is in the first term, containing no derivatives of delta functions, the Courant the Dorfman bracket on the generalized tangent bundle appears. And the second term containing the derivative, one derivative of delta function, the pairing of the generalized tangent bundle appears. This is the structure of a Courant algebra. So Alexey-Strobel current algebras can be described in the language of digit symplectic geometry. Moreover, Poisson algebras on the mapping space and n-dimensional manifolds from n-1 dimensional manifolds to degree n digit symplectic manifolds were constructed. And they are called Batani-Fradkin-Vilkovitsky current algebras. And this is the form. Here, epsilon is the test function of T1 sigma n-1. And alpha is in the degree n digit symplectic manifolds, and phi is in the mapping space. The current is of the form, and the Poisson algebras is given by the second formula. In the first term, containing no derivatives of the test functions, the derived brackets appears, and in the second term, containing the derivative of the test functions, the ordinary graded Poisson bracket appears. That is the point. And these current algebras can be seen as a higher generalization of Alexey-Strobel current algebras. And next, I explain an algebraic generalization of the BFV currents of higher Poisson vertex algebras. This is the Alexey-Strobel current algebras. And this term gives a Courant algebra. And the relation between Alexey-Strobel current algebras and the generalized tangent bundle is, and there is an algebraic generalization of the generalized tangent bundle and Alexey-Strobel current algebras. And the algebraic generalization of Courant algebras is the Courant-Dorfman algebras. And an algebraic generalization of Alexey-Strobel currents is the Poisson vertex algebras. Inspired by the Alexey-Strobel results, Extran gave weak random algebras from reconformal algebras and showed that the graded Poisson-Vertex algebras generated by elements of degree 0 and 1 are in one-to-one correspondence with the Courant-Durman algebras. And this is the definition of the Courant-Durman algebras. And this definition is given by the extracting the algebraic structure of the ordinary Poisson bracket and the derived brackets of the associated degree to DZ symplectic manifolds. And Poisson-Vertex algebras is a commutative algebra with a derivation, and the lambda bracket is satisfying some compatibility conditions. And the externalist shows that the Poisson-Vertex algebras that are graded and generated by elements of degree 0 and 1 are in one-to-one correspondence with Courant-Durman algebras. And we can see this theorem as the algebraic generalization of one-dimensional BFV current algebras whose target data are degree 2 DC symplectic manifolds. So we can consider a higher version of the relationship between Courant-Durman algebras and Poisson-Vertex algebras, which is the algebraic generalization of degree n DC symplectic manifolds and BFV currents. An algebraic generalization of functions of degree n DC symplectic manifolds are higher Courant-Durman algebras, and an algebraic generalization of BFV currents are higher Poisson-Vertex algebras. This is a higher definition of a higher Courant-Durman algebra, and this definition is given by extracting the algebraic structure of the ordinary Poisson bracket and the derived brackets of the associated degree n DC symplectic manifolds. And higher reconformal algebra and higher Poisson-Vertex algebra can be defined as the ordinary Poisson-Vertex algebras. And we can show there is a one-to-one correspondence between these higher Poisson-Vertex algebras generated by elements of degree from 0 to n-1 and extended higher Courant-Durman algebras. This is an algebraic generalization of the relation with degree n DC symplectic manifolds and BFV current algebras. And lastly, I will some comments about double Poisson analog, which is work in progress. A symplectic structure or a Poisson structure is defined on a commutative algebra, and there is a non-commutative analog, bisymplectic structure and a double Poisson algebra. And there is a definition of a double Poisson algebra. And for bisymplectic geometry and double Poisson algebras, DG, a bisymplectic analog of DG symplectic geometry and a double Poisson analog of Poisson-Vertex algebras were defined and studied. And the non-commutative analog of the one-to-one correspondence was shown. There is a one-to-one correspondence between graded double Poisson-Vertex algebras of degree -1, pre-generated in weights 0 and 1, and double Courant-Durman algebras. We can, using the techniques of the last section, we can expect the higher generalization of the correspondence can be constructed in terms of DC bisymplectic algebras like the ordinary Poisson-Vertex algebras case. But the physical meaning of this algebra is less ambiguous, so I want to understand more clearly. And now that talk is over. Thank you for listening.
Thank you for your talk. Is there any question or comment? How about online? Then, can I ask one question? I'm Yanagida. In the last part, so yeah, the ongoing work there, yeah, this story looks very natural and how to say, very natural question. And natural project, I think. But it is a little bit too abstract. And is there some nice or interesting example of this?
Uh, DC by symplectic algebra, the main example of DC by symplectic algebras are path algebras of double quiver.
Yeah, so that one is studied by Vandenberg, I think.
And
Concerning some chiralization of that path algebra.
and so
But anyways,
the
yeah.
double post matrix algebras were defined and studied to take a non-commutative analog of Hamiltonian PDEs. So
And on that, digit by symplectic algebra, then by this theorem, we have some double Coulomb algebra, right?
yes.
That double Coulomb algebra is already known, or how to say, just abstractly known one.
The non-commutative analog of the generalized tangent bundle is constructive.
And using that
called the linear exact double Coulomb algebraic dice. I remember.
But anyway, so you are considering the higher generalization of this story.
Yes.
I see. Yeah, thank you for your comments. And is there any other question or comment? Is it okay? Then let us thank Hayami-san again. And today's session is over. So thank you very much for all the participants and all the speakers. Hayashi Sensei, do you have some announcement?
So thank you for a nice discussion. So tomorrow, our workshop will start from
9:30 in China.
9:30 in China and in Japan 10:30. So okay, so now we want to move to